inductive teaching by interacting with CDIO projects. So I'm not really going to talk about the CDIO projects. I'm going to talk about how I interact with it in a traditional course. And I promise you that I do have some beautiful overheads, which you may actually get a chance to see. But I would say that I have, well, I can say, well, okay, this is going to be a presentation that you can remember. The first step we might say is, what is it we really need? Well, we can ask the industry, and they will say something like, well, we need engineers who can actually think as engineers, who have a basic engineering knowledge. They don't ask for advanced knowledge. If these guys would just understand the basic stuff, they would be very pleased. Then they want personal skills and communication skills. What? I stuck my... well, yeah. Basic engineering knowledge, personal skills, communication skills, those I'm trying to use here. We know that Danish industry want that. We know that everybody who have asked their national industry the same questions have got the same answer. Then what is it we want as teachers? Well, we want the bright students. We want enthusiastic students who work hard and independently, who can take initiatives and understand the basic stuff, and perhaps start to think as engineers. And in a way, you could have asked a teacher the same question 5,000 years ago, and he would have given you the same answer. Det er med elendigt. We can easily do that, and if we are in a perfect environment where we have plenty of resources and not that many students. And I'm not in that situation. I can tell you that at my institute, we don't just teach civil engineering students, we have also building engineer students that we let in twice a year. That's the Kingston. NCI, no, the one that marked, yeah. There, and you open this one. And some life will be created there. Well, thing is, we teach 4, 5, 6 different types of engineering educations, and they all need brilliant. Yep, and I. No, I'll just. No, you are absolutely right. It doesn't work. Well, anyway, let me have the keyboard. Yep, that was the first one. I skipped to. You see this list. These are all the different educations we have, and they all have to learn about basic concrete structures. We have lined up 3 different course numbers. You're most welcome to have that. I'll use my arm and the keyboard. Yeah, never mind that. I hate the laser pointer. You see, I have to teach them all the same topics. However, for all of them, in the semester I teach them, they have a CDIO project or a similar project. These projects do not have the same content. In some way, it's pure hell to teach the classic course and have it combined with these things, but it works and you can have a good interaction. I'm only going to talk about the interaction with this project. One of the things you have to work with when you have many different types of students is different types of students are interested in different things, and you need to find out what can motivate them. And here, I would say, you try to figure out what can motivate them all, and what can stimulate their engineering thinking. And, well, I've tried something. moved away from the more deductive approach where you say, well, look, this is the variation of the strains, this is how you can calculate in this stage and in this stage and then in this stage, etc. This, I'm not really criticizing that. That was how I was taught. But I thought, well, we will approach it in a different way. We will start every session of 4 hours with a demonstration or a video or pictures of the phenomena we're going to work with. I mean, why not show the students the things in reality before you go to the beautiful drawings from the textbook? It's both a part of a sales speech and step one in COP's learning steps. You know, the why, what, how, and what if. And I'm going to show you an example of how we do it. And I don't know if I'm getting a few minutes extra for the confusion, but I'll do my best. Step one, why? I mean, this is really, why on earth should you listen to this lecture? Why should you be interested? Well, we can take the case here. We have a student who is testing the beam, and when he put enough load on, then of course we have a failure. Here we have a bending failure. Now, if you work with concrete beams, you have two options now. You can either just test all your designs. It's going to be bloody expensive. And it's difficult if you build a bridge to have a full-scale testing. So this is why you need to figure out how to calculate this capacity. Of course, step two will be figure out what is happening here. I had some students who created a video. When they do testing for capacity, it's a brilliant idea to have to make a digital video. They can use their own cameras, by the way. We put the video of this central part of it out on YouTube. It takes 5 to 10 minutes. I'm not spending 5 to 10 minutes in a course showing them a video because I think this is a waste of time. They can look at themselves. But we can take the genuine data that we measured, the relationship between the curvature, I mean how much the beam bent, and the bending moment required to bend it. And we can have this real curve, not just something drawn in a textbook, but really a real curve. Of course, an experienced civil engineer can tell you a lot of things by just looking at the curve. Students are not experienced. So we pick another approach. We look at these different points, say point A, we are here, the end of the linear relationship. Something must be happening here to change it from linear to be curved. And what happens is, of course, it starts to crack. I don't know if you can see the cracks. If you can't see the cracks, then it's not because your eyes are old, it's because you've just started to crack. Let me increase the deformation a bit. You see the beam moving, you see the cracks opening. These crackings is what makes the beam less stiff. And I can increase the deformation a bit more and reach this maximum point. Maximum bending moment is what we call load carrying capacity. This is as much as it can take. And obviously, if we use our common sense, we can say, something else must be happening here. Otherwise, it wouldn't drop. So move to point F, and you start to see some new phenomena, which must be what kills the beam, and you can go on and see how it develops. Now, with my students, I have as much time as I like. So I would normally take the video from point E to point H. That's 37 seconds to show them how smooth and plastic this failure is. So this is what happens. Next step is, of course, to find out how can we analyze it. If we didn't have the testing, how could we estimate it? And I would normally leave this picture up on the screen. I would make a simple drawing of the crack patterns. And you might say, we would then be doing an autopsy of the failure based on our common sense, based on what we see. And then we can argue, well, if we have such large cracks up here, we probably can't transfer any force in this direction except in this steel bar that's up here. Steel bar is very deformed, so it must have reached its maximum possible stress, that is the so-called strength. Down here we have something else which we would use our simple common sense to say, well, it's probably like this. And then we can look at equilibrium, we can calculate the bending moment. I would say you can all do that. You all went through college, I suppose. This is essentially one of Newton's laws. You had to add the forces up to 0 or the cross-section is going to accelerate. You can estimate what would the bending moment be here. And you know what? This simple formula is what is used for at least 98% of all concrete beams to design it in bending. And you have derived that just by looking at the video and using your common sense. I was a little afraid the first time I used this because I had only one reason to use that test and that video. That was, I just didn't have the resources and the time to do the testing myself and hire a professional photographer. Turns out the students actually like it. They feel such things are very real, much better than computer simulations. And we have kept mathematics on the lowest possible level until they have understood the basic things. A few other signals that I sent with this is, of course, their work matters. I prove it because I use their results in front of hundreds of students. It also proves to them that my course is actually relevant. They're going to use it later this semester and forever after. Then, of course, step 4 would always be, what if? What if we didn't have the test? What if we want to calculate like that? And again, you can use the things you can derive from this simple explanation to really limit the use of the theory. And then, of course, you have to discuss, what if we use other concretes, other designs, etc. So it's really back to the basic. It's start with reality and then move slowly into the theory. The textbook, a classic textbook, is all about theory. Yeah, so this is essentially how we develop things. I think it's a good idea because we clearly link reality to theory. This is what engineers must do. That way of ending up and saying, well, this is the failure we need to calculate on. Well, quite frankly, this is how all the theories have been built up. We do not make theories for anything if we don't see a problem. Did it work? Do they learn more? Well, difficult to say. Motivation, at least. They like this approach with the inductive. They think it motivates them a lot. Okay, I can't distinguish if this is the effect of the inductive approach or just because they like my show. It's probably a bit of both. I had 2 colleagues who from time to time takes the same lecture and follow another approach. They like them too, and their approach too, but not that much. So yes, I think this worked with the students. I've got one overhead left. Good. Thank you very much. This was about student motivation. I have to say, students are not the only ones who work at the university. There are also all our colleagues. Are they all in favor of the CDIO-projects? No, they're not. Because we spend a lot of time and resources on the CDIO-projects. I think it's a wonderful idea. The students spend a lot of time on it, and that's sometimes give a bit of grumbling. And therefore, you really need to consider how to motivate your co-workers, because we all say we have courses that support the CDIO projects. That's fine, but that's not cooperation. Real cooperation is when both parties do some work and both parties benefit. And I would very much suggest that you make sure your CDIO projects give something back to the supporting courses. In my case, I got a wonderful video and good test results. I can use that. And, well, unless you are in a place where you have plenty of resources, then you really need to consider this sign here. You need to cooperate and collaborate, or some of you will die of overworked working, and the CDIO concept will also die. If you give them something back in return, you make them better, you make them more loyal, you turn their courses toward the CDIO concept, and this is what we want. Thank you very much for the tolerance, and I hope the next...
For less than 15 minutes.
What?
You only spoke for 14 minutes. So okay, so
yeah.
another one or two questions. We are a little bit behind, but I'm going to tolerate because of the cock up at the moment.
Yeah.
Any questions? I've got one while the others are
yeah.
thinking. How many students, in front of how many students can you crack the beam? You spoke later on of 100 students, and you can't stand 100 students.
The wonderful thing is, I don't crack the beam in front of the students. I have the video, I show the pictures, I have the beam that roll in, because I'm not allowed to...
They don't actually see the real thing happen.
No.
It's still well, not a simulation, but a...
No. It's extracted picture and there's a link to the video. Sorry. And one of the groups later do similar testing. The other groups don't. Well, I can say there were 225 students lined up for the courses. So,
I mean, just a comment on your final couple of slides. I do think you're perfectly, properly self-critical in saying we can't tell the difference between the students liking it and learning it.
No.
That's a recurrent problem.
And I have really been thinking, I'm sure we all have been thinking, if we do this or that, how can we test if the students learn more? And I would say, well, it's bloody difficult.
It's difficult, you're right, absolutely. Okay, we've still got work to do. So thanks very much.
Yep.
Okay, so the next paper